In this video, we are going to introduce the concept of chemical bonding. Now, a chemical bond essentially holds together two different atoms. We have illustrated here, and it turns out that there are different types of chemical bonds. And so in this video, we want to go ahead and introduce three major categories of chemical bonds that basically describe the different sorts of interactions between these two atoms. Essentially answering that question, what is it that's holding together the different atoms in these three different types of bonding interactions? Now, to do this, we're going to have to go back to our previous lecture on electron configuration and recall that there's this concept from quantum mechanics that tells us that atoms like to have a full outer shell. So if we look at, for example, the electron configuration of neon, illustrated here in this energy diagram, we see that neon, that second row element, has a full outer shell. Okay? So the n equals 2 shell is the outermost shell, and we can see that it is fully occupied by 8 electrons. Okay, and we talked about previously how this configuration is favorable from an energetic standpoint, and as a result, when you are forming ionic compounds from, say other second row elements like nitrogen, oxygen, fluorine, we could actually predict the charge for those ions using this desire to, quote, look like a noble gas. What we're going to do in this lecture is predict the formula and structure of molecules. And really this will actually form the foundation for this whole mini-series. Use this same concept of filling up this outer shell to essentially go beyond just looking at ions on ionic compounds, but actually look at structures and formulas of compounds more generally. Okay, so with that in mind, what I want to do is give you a quick overview of the three different broad categories of chemical bonding interactions. So the first type of bonding interaction, we've actually had a little bit of experience with this when we had our discussion previously regarding formation of ionic compounds. We talked about how, for example, if you have a metal and a non-metal and you bring those together, typically what will happen is that metal will give an electron to the non-metal, resulting in the formation of a positive and a negative charged ion. The magnitude of those charges can differ, of course, depending on what metal and non-metal you're working with, but at the end of the day, that metal and a non-metal coming together is the result of simple electrostatic attraction between those positively charged cations and negatively charged anions. And you can get these nice ordered lattice structures like you see here for sodium chloride, or just simply table salt, where you have this altering arrangement of the little purple sodium plus cations and the green Cl minus anions. So basically you have formal charges being formed on each one of these ions and attraction between the positive and negative charges. All right. Next on the list is so-called covalent bonding. So covalent bonding is a bonding interaction where you are typically involving two non-metal atoms. And if you have two non-metal atoms, remember both of these atoms then have a relatively high affinity for electrons. And as a result, those electrons aren't transferred fully from one atom to the other, but rather the electrons are shared between two atoms. So the sharing of electrons is sort of the defining feature for a covalent bond. And then last, our third type of bonding, and one that I'll mention here and we're not going to discuss again at the introductory level, is this idea of metallic bonding. So it turns out that if you have a metallic substance, what ends up happening is those outermost electrons actually become associated with the entire sample, and they can essentially float around in what is oftentimes referred to as an electron sea. They're allowed to move around the whole length of that metal, and this gives rise to some important properties that we associate with metal, namely their conductivity, the metallic luster, even malleability. So very interesting physics and chemistry going on there. But like I said, we're not going to talk about metallic bonding anymore at the introductory level. it's something to look forward to in your future studies. Okay, so let's go ahead and focus in on the two types of bonding that we're gonna really care about here, ionic and covalent, starting off with a discussion of ionic bonding. So as I said, ionic bonding is defined as an electrostatic attraction, right, between two ions formed through the transfer of one or more electrons. So we saw on the previous slide this example of sodium transferring its electrons to chlorine, and what ends up forming is this ordered lattice structure where the positively charged sodiums are attracted through electrostatic interactions to that negatively charged chlorine. Okay, and metals or nonmetals, metal and nonmetal interactions are kind of the hallmark for ionic bonding. They're not all ionic bonding, but a good chunk of it, because of this fact that metals have this lower affinity for electrons relative to those nonmetals. So they basically have a tendency to transfer electrons from that nonmetal to that metal. And this key word here, transfer, is really important for ionic bonding, right? So if we want to define the distinguishing feature of an ionic bond, it's a transfer of electrons, formation of these distinct ions, and then those ions are attracted to one another. Okay, so this idea of transferring electrons and keeping in mind this octet principle, this desire of atoms to have a full outer shell, allows us to predict the chemical formula for ionic compounds. So the method for doing this is relatively straightforward. It's a simple, two-step process. The first step is to determine the common charge each element will take. Okay, and so let's go ahead and do that for our example down here. So step one says, we're going to look at sodium chloride, and we want to determine the common charge that each element will take following that octet rule. Well, if you go back to that periodic table, sodium is going to want to look like neon, and it's going to want to take a positive charge. So I'm going to put the charge up here in black, and then chlorine is going to want to, once again, look like a noble gas, grab one additional electron to do so, and it'll have a negative charge. And so we've formed a Na plus and Cl minus. And then the second step is to determine the number of each of these resulting ions required to come together to form a neutral compound. Now this example is relatively straightforward because the sodium is a +1, chlorine is a -1. So if you have one of each, then you have a neutral compound, NaCl. Okay? And so as a result, sodium chloride, as we already know, has the formula NaCl, and it's the result of this Na plus and Cl minus ions, right? So directly balanced. Okay, but things can get a little bit more complicated, and there's many instances where we don't have a simple 1-to-1 ratio. So to understand that, let's look at a example that we haven't seen before, and let's try and predict the formula for sodium sulfide using this method outlined at the top of the slide. Okay, so the first step, we need to determine the common charge for each one of these elements. So for sodium, once again, we are going to be looking at forming an Na plus, and sulfur, just below oxygen in the periodic table, will tend to take a 2- charge. Okay, so now we're in a scenario where if we were to just take one sodium and one sulfur, the resulting ionic compound would then have a -1 charge, right? And our goal is to form a neutral compound, right? So you then have to ask yourself, well, what ratio of ions is required to form that neutral substance? And so many of you might see from inspection that, of course, what you're going to need to do is take 2 of these sodium atoms and one of those sulfurs in order to get the ratio that gives an overall neutral ionic compound. And now there's a little trick here I want to show you guys that allows you to arrive at the same answer and help you identify the pattern or the relationship and number of different ions required to form that neutral compound. And it'll come in handy when we get to more advanced problems. So notice what I did here is I once again drew out the sodium and sulfur ions with the respective charges. All right. Now, typically we just write plus, we don't put a 1 plus, but I drew out the 1 to highlight this approach. And so the approach really boils down to looking at those ions and looking at the number, the magnitude of the charge on each one of those ions. And if you want to form a neutral compound, what you do is basically do this little crisscross approach. You take the magnitude of the charge for one of the ions here, so for sulfur it'd be 2, and then you bring that down as the subscript, which will determine the number of atoms for the other ion, right? And then vice versa, we'll take the charge, the magnitude of the charge for sodium, and take that down, it'll be the subscript for the other atom, sulfur, and that will then give us the exact same chemical formula we obtained before, which is the chemical formula for that neutral compound. So let's look at a final example here where that crisscross method will really come in handy. So in this example, we're asked to predict the formula for aluminum oxide. So once again, we'll write out our aluminum and put that charge on there. And so the charge on aluminum will be a 3 plus, and then it's an oxide, so it's going to be oxygen, and that's going to be a 2 minus. Okay, so the question we want to ask is what ratio of aluminum and oxygen atoms, or ions rather, are going to be required in order to form a neutral compound. Well, you could find that least common multiple, or you could just do the little crisscross method here. Take the 3, magnitude of the charge on aluminum, move it down as a subscript on oxygen. Take the 2, magnitude of the charge on oxygen, move it down as a subscript on aluminum. All right. The result will then be a Al2O3 compound, and that will then be the smallest whole number ratio of aluminum oxygen atoms required in order to form a neutral compound. Okay, so that rounds out our ionic bonding discussion. And so remember, ionic bonds involve this transfer of electron, formation of charges, and then those charged ions stick together via electrostatic forces, right? And so we've seen how we can use this idea from quantum mechanics, wanting to have that full outer shell, in order to predict what ions are going to form, and then based on those predicted ions, determine the ratio of atom types that are going to be present in the resulting ionic compound. Now we're ready to go ahead and start our discussion of covalent bonds. Okay, so covalent bonds differ from ionic bonds in that rather than transferring electrons, in a covalent bond, the electrons are shared between 2 or more atoms. Okay, so their atoms are kind of playing a tug of war, if you will, with those electrons, and those electrons are kind of moving around in between them, and of course they will exist in orbitals. We'll talk about that later on and the ramifications of that later on. But at this first pass, we want to really think about this concept of sharing electrons. Electrons involved in a covalent bond will be associated with both atoms, not transferred. Okay, and this will typically happen between nonmetal atoms. So as you recall, nonmetal atoms tend to have high affinities for electrons, and so they still want to have that full outer shell. We're still going to rely on that concept of octet rule and filling up that outer shell. But when these atoms are working to fill up their outer shell rather than transferring and giving up and gaining electrons, they're going to tend to come together and form different structures where these electrons will be shared. And so if we analyze the result of the sharing electron, we can start just on some very basic arguments here. Use this fact that electrons are attracted to both nuclei to come up with a mental picture of where these electrons are likely to reside. Okay, so if you've got two nuclei here, in this case it's two protons, right? And I've got three different illustrations here, and you've got an electron that's going to be associated with both of those nuclei. Well, the lowest energy configuration is going to be the configuration where that electron is positioned between both of those nuclei. If the electron is very far off center or very far, off to one side or the other, right, then that will decrease, the stability of this configuration. And so putting those electrons in the middle, which essentially lowers the energy, reinforces this concept of sharing those electrons. Okay, and I want you guys to remember, we're not going to really come back at the introductory level and think about orbitals in this more advanced context, but I want to at least throw up a little reminder here that when you are forming covalent bonds, you are taking electrons that are existing in orbitals. So in this case, we've got an orbital on this carbon atom in purple, orbital on this hydrogen atom in green, and you've got electrons in those orbitals. And so if you are sharing electrons, what you're effectively doing is overlapping these quantum mechanical orbitals, and you're forming a new orbital that is basically associated with both atoms, both the hydrogen and carbon in this example here. So we're not abandoning our discussion of quantum mechanics and orbitals. We're basically extending that concept to build what we end up calling molecular orbitals associated with molecules. Okay, but what we're going to actually do here is, rather than draw out those orbitals, because as you can see, even for a simple molecule, they start getting relatively complicated here, we are going to draw out a structure that looks like this, where I'm going to use a single line to represent a shared pair of electrons. Okay, so two electrons that are associated, shared between these two nuclei, is represented by this single line, and that's going to be what we use essentially throughout the rest of our introductory discussion of molecular structure. Okay, so then, just as we saw for ionic compounds, the real application of understanding covalent bonding is going to be predicting chemical formulas, and as we'll see later, even chemical structures, using some basic tools, right? And it turns out we need a couple tools to be able to predict the chemical formulas for a molecular compound. So the first tool that we're going to need to use is the counting of valence electrons. We absolutely have to be able to look at an atom, figure out what the highest n principal quantum number shell occupied by electrons is, and be able to determine the total number of those so-called valence electrons. And so before I move on, I want to ask the question, why is it again that we are going to be focusing in on just the valence electrons? So I want you to pause the video for a second and see if you can answer that question based on what we talked about in the previous lectures. Okay, so hopefully you came up with an answer somewhat related to those valence electrons being the outermost electrons. And those outermost electrons, I like you to think of them as the atom's clothing. It's what the atom shows the world. It's going to really be dictating the types of interactions that atom has with the external world. So what kind of bonds it forms is going to be largely directed by the number and type of valence electrons. The core electrons are going to be inside so closely that we really don't see them. So they're held really tightly to that nucleus. I'm going to draw maybe two of them here, that they're not shared, right? To a very good approximation, they're not shared, and the outside world doesn't even see them. So all we care about is those outermost valence electrons when we're talking about bonding. Okay, and so what we're then going to need, which we've talked about valence electrons before, but what we're going to need then is a set of rules for building covalently bound structures that involves a sharing of electrons. And these structures are called Lewis structures. And so what we're going to have to develop in the next lectures are rules for building these so-called Lewis structures to be able to predict chemical formulas for covalently bound compounds.